I'm going to talk about charge carrier transport in semiconductors, and we'll specifically be looking at semiconductors with reduced dimensions. These are semiconductors which have restricted motion of the charge carriers in one dimension or the other. And you might ask why these studies are useful or relevant. So to answer that, I want to refer to the Moore's law. And I guess all of you are familiar with that law, as per which the size of the transistors are shrinking fairly rapidly, right? And most of these transistors have in fact become transistors with reduced dimensions. So it's very important that we have a good understanding of the physics of charge carriers in these low dimensions. And that forms like the major application-based motivation for these kind of studies. They have fundamental importance obviously it's fundamentally important to understand what's going on in low dimensions, but from an applications point of view, it's important to understand because you can use that knowledge to improve transistor performance. Okay, so this is an overview slide which talks about what I'll be going through today. So I'll give a brief introduction to low dimensional systems and how these are nanofabricated in the clean room. And then we'll look at some external effects. We'll focus mostly on a two-dimensional system, a two-dimensional electron system, and we'll look at some external effects on these systems, which means application of an electric field and magnetic field. And then we'll move on to some quantum effects that exist in these systems. Okay, so this slide here just introduces the concept of reduced dimensions. So anything that you come across in your everyday life is essentially a three-dimensional object, right, as shown here. And the electrons in this system, they are free to move in X, Y, and Z direction. So it is possible to fabricate systems which have restrictions imposed in one dimension or the other. For example, this one, it's a two-dimensional system where the electrons are just free to move in the XY plane, and the Z dimension has been constricted. So this system is called a quantum plane or a two-dimensional electron system. It's possible to restrict the motion even further. And when we do that, we get a one-dimensional system called a quantum wire. It's a 1D system, and we refer to it as a quantum wire. Following on from this, it's possible to restrict movement in all the three dimensions. And what we get in that case is essentially a puddle of electrons. We call it a 0D system, a zero-dimensional system, or a quantum dot. So these are the three different kinds of reduced dimensional semiconductors that we can fabricate. So let's look at some physics of these systems briefly. So we always start with the time-independent Schrodinger equation. I guess some of you must be familiar with this equation. So if you consider a free particle which is not under the influence of any potential, you have V equals 0, and you solve the Schrodinger equation, then the energies for a free particle look like this. Can you see my pointer?
Yeah.
Yes.
Okay. So the energies for a free particle are given by this expression here, where K is the wave number, and the only restriction on K is that it has to be a real number for energies to be positive. That is the only restriction here. So a free particle is allowed to have any energies as long as it satisfies this equation. But in a two-dimensional object where you have constricted motion in the in Z direction, but you only have free movement in X and Y, then the energies in the constricted dimension become quantized. If you look at this expression here, this is the expression for the total energy of such a system, but the energies in the Z direction become quantized. And we call this energy quantization in the Z direction. The energies in the X and Y direction are again given by the same expression, but K is only allowed to have, K is a wave vector, so it's only allowed to have values in the X and the Y direction. If you look at this expression again, then you'll also see that I've replaced M with m star. M star is the effective mass. When an electron moves in a periodic potential, then the free electron mass gets replaced by an effective mass due to the periodic nature of the potential. So the free mass gets replaced by an effective mass in this case. And then, sorry. And then if we move to a 1D system, if you confine the motion even further, then you end up having quantized energies in z as well as y direction, and you only have free motion in the x direction. So the main take-home message from this slide is that if you impose restrictions on the movement of carriers in one dimension, then the energies in that dimension become quantized. There exists a series of subbands in 2D and 1D, and that represents energy quantization in the dimension that has been reduced. So this slide over here shows the density of states versus energy diagram in different dimensions. The density of states is a very important concept because it allows us to calculate the density of a system. It gives us the number of states allowed per unit energy. And so if you look at the different traces, the blue one is for a 3D system, and you can see it. We are allowed to have a continuous density of states in a 3D system. But for a 2D and a 1D system, you have these series of steps that represent the subbands that I was just talking about. So in 2D, you have this staircase-like structure, which represents the first subband. And then once this subband is full, then the carriers have to go on and move on to the second subband and so on. And the density of states for a 1D system is also like a step function where you have these quantized 1D subbands. So I've given some background on the physics of these reduced dimensions. So now let's talk about how do you fabricate these reduced dimensions in the lab. So conventionally, most of these 2D systems were developed in heterostructures, which means at the interface of two different semiconductors. And I worked quite a lot with gallium arsenide, so I'm going to give you the example of a two-dimensional electron system in gallium arsenide. So the system is grown using a technique called MBE, or molecular beam epitaxy. And the schematic here just shows the fabrication of a 2D quantum well. So you start off with a gallium arsenide substrate, and you have these things. These are called effusion cells for MBE. So you open up the gallium and the arsenic effusion cells, and you grow a layer of gallium arsenide, followed by a layer of aluminum gallium arsenide, which we call AlGas. And then we dope the AlGas layer with silicon, and this layer essentially provides the electrons. This is the layer which has been doped heavily with silicon, and this is the provider of electrons. But these electrons actually, although they are provided by this AlGas, they prefer to go and sit at this interface. So the electrons come from here, but they prefer to sit at this interface between gas and AlGas. And that is because of the differences in the band structures of gas and AlGas. Gas has a band gap which is lower than AlGas. So this is how the structure looks like. You have donor atoms here, and they give out the electrons, which prefer to sit at this interface because it's lower in energy than this interface over here. So what results is a 2-deg, or a two-dimensional electron gas. And this technique of producing a 2-deg is called modulation doping, where you have the carriers are spatially separated from where the 2-deg resides. So this technique was developed quite a few years ago, and it's been studied quite a lot. Yeah, so this is one of the ways to develop a two-dimensional electron system. If you want to restrict the motion even further, for example, if you want to make a 1D wire, then you start off with the 2-deg in gallium arsenide, and through clean room methods, you can form a quantum wire in this system. So I don't know how many of you have a background in in clean room processing, but I'll just walk you through some of the steps of how you would fabricate a 1D system from a 2D system. So you'll start off with the 2DEG in gallium arsenide. You'll spin coat this substrate with photoresist if you want to do photolithography, or PMMA if you want to do EBL, electron beam lithography. And you pattern the photoresist using a chrome-plated photomask. You expose the unmasked regions of the photoresist with UV rays, followed by development. So whatever was shown to UV light has been developed away. So you basically form a mask of photoresist, and you can then etch away the gallium arsenide in these regions. So you see the gallium arsenide has been etched in these regions. And so basically this, if you look at the cross-section, it's hard to see. So if you look at the cross-section really, then this forms a one-dimensional system. You already had a 2D system where you didn't have motion in the Z direction, but through this etching, you've essentially created a 1D system now. So these are the different ways of producing low dimensions in the clean room and using growth techniques of MBE. But I want to quickly talk about these new class of materials called 2D materials, which I'm sure most of you work with. They are intrinsically thin, atomically thin materials. So by default, these materials have a two-dimensional electron gas system in them. And they are systems like graphene, TMDs like MOS2, WS2, WSE2, even MXenes, which is another system that I work with here. For example, silicene, which is a two-dimensional sheet of silicon, phosphorine, a 2D sheet of phosphorus, and so on. So these are new materials which are intrinsically 2D, and they host a two-dimensional electron gas in themselves. So before I move on, are there any questions at this point? Okay. So we are now going to look at some external effects. We are going to now focus on just a two-dimensional electron system, and we'll look at what happens when you apply an electric field or a magnetic field to such a system. So, okay. So consider a 2D sheet of electrons with nothing done to it, and you have the system at room temperature. So the electrons in this system are subjected to a lot of thermal noise. They're moving around quite rapidly because of heat effects. And this is called just thermal motion, rapid thermal motion of the electrons. If you want to have a motion of the electrons in a certain specific direction, then you have to apply an external electric field. When you apply an electric field, then the electrons acquire what is called a drift velocity, given by this expression here. And the drift velocity is opposite in direction of the electric field, which is why we have this minus sign. So this is an expression for the drift velocity. This term over here, represented by the symbol torr, is the transport relaxation time. It essentially is the time between two consecutive scattering events. There are lots of impurities and other electrons in the system. So an electron scatters off from other impurities and other electrons, and torr represents the amount of time that the electron travels between two consecutive scattering events. So this is an important quantity for 2D systems. Then we look at the electric current density, which is the electric current per unit area. And by definition, it's given by this expression over here. Sigma is the conductivity of the 2D material. So we in this expression, we just put the value of Vd, the drift velocity, and we get an expression for the conductivity of a 2D electron system given by this expression over here. An important quantity for any semiconductor system is the mobility of the system, given by mu, the symbol mu. This is the definition of mobility, and we can substitute, if we substitute the value of Vd here, then we can extract the value of mobility, which is given by this expression, which is very important. We'll come back to it later. So mobility is a very important property for any conductive material. It is a measure of how quickly the electrons move under the influence of an electric field. But it's really independent of the electric field. You see in this expression, it's a property of the material that is that you're looking at. So it only depends on the mass of the electrons in that material and the relaxation time. It's completely independent of the electric field. So just keep in mind that mobility is a very important quantity for semiconductor systems. So we'll now look at the effect of a magnetic field, and we'll only be talking about an out-of-plane magnetic field. You have a 2D system, and you apply a field which is perpendicular to this 2D system. And these studies are called magnetotransport studies. It's a very important term that you'll come across in the future, I'm sure. And it basically means transport in the presence of a magnetic field. And it's a very important tool for extracting some important quantities of a semiconductor system, as we'll see. So if you have a system, you have a 2D system, you've applied an electric field in the system, and you apply an out of plane magnetic field, then the electron experiences a force called the Lorentz force, and it's perpendicular to both the electric field and the magnetic field. So I think this is called the Fleming's left-hand rule, where you can find out the force that acts on a charged particle. So if you have electric field in this direction and B field in this direction, then the electrons essentially experience a force in a direction which is perpendicular to both of these. Can you see my hand? Sorry, I'm on full screen, so I'm not sure if you guys can see this.
Yeah.
Okay, perfect. Thanks. Yeah, so this force is called the Lorentz force, and the best way to harness this force in experiments is through an effect called the Hall effect. I'm pretty sure some of you are familiar with the Hall effect. So this structure over here, it's shaped in a certain way, and this shape is called a Hall bar, where you have these X's, they represent ohmic contacts. The yellow thing is a 2D gas, a two-dimensional electron gas, and you put ohmic contacts to this electron gas to kind of contact the electrons. So if you flow the current in this direction and you have an out-of-plane magnetic field for this electron system, then the charge carriers will start to experience a force which will make them drag in this direction, which is perpendicular to both the electric field and the B field. And this essentially, the collection of electrons in this direction gives rise to a potential which is called the Hall voltage. So you develop a transverse voltage in this direction, and we can measure it in experiments, and it's called the Hall voltage. Another important aspect of the application of a B field is that, let's ignore the electric field for a second. If you just have a charged electron and you apply a B field to an electron, then it starts to execute circular motion, and it moves in a circular trajectory with a frequency called the cyclotron frequency, given by this expression over here. And the frequency is a function of magnetic field. So again, this is an equation which we will come back to. Okay, so this sets some fundamentals of the Hall effect. So the Hall effect is a very important tool for anyone working with low dimensions, because it helps us in extracting some useful quantities, for example, density and mobility in a 2D sheet of charge carriers. So because of the Hall effect, the current is no longer just in the direction of electric field. You have carriers accumulating in this direction as well. And because of that, the conductivity and the resistivity is no longer a scalar. They become tensors. You can think of tensors as just vectors, but with more than one direction. So the conductivity develops components in both the longitudinal direction as well as the transverse direction, and the same with the with the resistivity as well. So conductivity, resistivity become tensors, and we'll derive some relationships now. So the transverse resistivity is related to the longitudinal resistivity using this expression, where omega c is, remember this cyclotron frequency that I just talked about. If you look at the current density in the x direction, which is this direction, then that's given by the current flowing in the x direction and the width of the Hall bar. This is just by definition of current density, which is current per unit width. And then we also find out the electric field because of the Hall effect. So this is the electric field in the y direction, which will be given by the voltage developed in the y direction divided by the width, right? And using these two expressions, we can find out the resistivity in the transverse direction. Again, this is the definition of resistivity. So you just divide these two quantities and you get a result which is very important for 2D systems. It basically means, so you get rid of the width of the Hall bar. The Hall resistance is the same as the Hall resistivity for a 2D system. And this is a very important result for 2D systems. So let's keep this aside for a second, and then I'm going to use equation 3 and 7 in equation 8. Let's look at equation 3 and 7. So equation 3 is the definition of conductivity. I guess we reverse it to get the resistivity. And equation 7 is the cyclotron frequency expression. And we substitute both of those equations in this equation over here. So we substitute the value of longitudinal resistivity and the cyclotron frequency, and we get an expression for the transverse resistivity. Solving this further, we've just found out that the resistivity is the same as the resistance. And we've reached a very important conclusion, which is the density of the charge carriers is inversely proportional to the Hall resistance. So we define a factor here called the Hall coefficient, which is just the fraction of Hall resistance and the B field. It's called the Hall coefficient. So we substitute Rxy over B for Rh. And this is one of the most important results that you will find in the physics of 2D systems, which is the density for 2D systems on the basis of Hall effect. Hall effect is a very important tool because it gives you a way of finding out the density of charge carriers. And this is a formula that's really very significant. I use this quite a lot for calculating the densities of the systems that I work with. And moving on, you can use this to also find out the mobility of the system. So we go back, just going back from the previous equation of mobility, we rearrange this equation to get this, and then we just simply substitute the value of density that we've just found out, and we get a value for mobility as well. So these two expressions, I cannot stress enough how important these two expressions are if you want to work with 2D systems. You utilize the Hall effect that a 2D system exhibits to calculate the density and mobility of a 2D system, which depends on the Hall coefficient. Okay, so let's now move over to some quantum effects. So far, whatever I've considered about B fields has been in relatively small magnetic fields. You observe the Hall effect for relatively small magnetic fields. But if you start to apply very strong magnetic fields in a 2D system, then you will start to see some quantum effects because of the confinement that is there in the 2D system. So in the presence of strong B fields, you require a quantum mechanical description. And specifically when this condition is fulfilled, you start to see some quantum effects. So what does this condition really mean? This is the cyclotron frequency, and it has to be high, which means, and the cyclotron frequency depends on the B field, right? So if the B field is high, the cyclotron frequency will be high. So that criteria is satisfied. And the other term is this torque Q. which is the quantum lifetime. It's not the same as the lifetime, the transport relaxation lifetime that I talked about before. It's this lifetime deals with the amount of time that an electron takes to complete one full circle of the cyclotron trajectory. So this basically means that there is low disorder in the system such that the electron is able to complete one full circle, and the electron wave is able to interfere with itself and form new quantum states. So this is only used when you need a quantum description of the system. And this condition basically implies you have to have a big enough magnetic field, and you have to have a low disorder in the system to observe quantum effects. You don't expect to see quantum effects when you have a highly disordered, low mobility 2-deck. You have to have a very clean sample. So what happens when you apply a very strong magnetic field, and we're only talking about perpendicular magnetic fields, the energy in the z direction stays the same because that is quantized because of confinement things. But the energy spectrum of the particle in the xy plane is no longer continuous. It becomes a series of delta functions called Landau levels. I know this is a little bit hard to understand. So basically the energy spectrum in xy is no longer continuous, but that also becomes quantized, and we get this thing called the Landau quantization. This is a figure of density of states and the energy in the xy plane only. And these green pillars that you see are called Landau levels. This is an effect of quantization on the application of a very strong magnetic field. So the separation between two Landau levels is given by h cross omega c, and we label each of the Landau level with an index called the Landau level index, which is given by this number NL. And this Landau level index can only take on integer values. That's a requirement of this Landau quantization. I'll come back to this figure in a second. Another important expression is that each Landau level can hold only a fixed amount of charge carriers, which is given by this expression EB over H. So each Landau level holds a fixed number of charge carriers, which is a function of the B field. And also the separation between two Landau levels is a function of B field, because we know that omega C depends on the B field. So basically, when you increase the magnetic field, then each Landau level starts to hold more and more electrons because of this, and the separation between each Landau level also starts to increase because of this. We can use a term called the filling factor, which essentially represents the number of Landau levels that are filled. So let's say a new number of Landau levels are filled, and this is the number of electrons that each Landau level can hold. And the product of this...
excuse me?
Yeah.
I have a question. So physically, how can you present the Landau levels?
How can I?
Like because you say they're filled. What does that mean? Like, okay. I understand filling in the conduction method.
Okay. So these are, right. So this is a figure of density of states versus energy. When you look at the conduction band, those are essentially levels which are so close together that they form a band. But in this case, these energy levels are discrete. They have an energy separation. They have a separation between them. So these are discrete energy levels which hold a certain number of charge carriers. And once this level is filled, you have to move on to the next energy level. This is what quantization is. Does that make sense?
Yes. Okay.
I want to show, now that we're talking about it, I want to show a little movie which will explain this even further. So I just took this from Wikipedia. So let's not look at the right-hand side just yet, just look at the left-hand side, which represents the density of states and the energies. So I mentioned that as you increase the B field, each Landau level, these triangles are Landau levels. Each Landau level will start to hold more electrons, and they will also start to move further apart from each other because of the increasing separation. So this movie is as a function of B field. So see what is happening. The higher lying Landau levels are getting depopulated, and this movie doesn't show it, but each Landau level also starts to hold more electrons. Let's look at it again. This is the Fermi energy level, and when you increase the B field, the Landau levels basically move through this Fermi energy. Is this becoming clearer with the movie?
Yes. So essentially, your Landau level can fill more charge carriers.
Mm-hmm. Yes.
They are below that. So your total charge carriers are going to be the same, but the amount of Landau levels will decrease.
Correct. Yeah. The total number of charge carriers in any system stays the same. Say you start with an X number of charge carriers, and you fill the system. A lot of Landau levels are filled at that time, and you start to apply an increasing B field. And what you see is that the higher lying Landau levels will start to depopulate because more and more electrons will just stay populated in a lower lying Landau level. Right?
Yes.
Okay. So, right. So if you have an integer number of Landau levels filled, this expression I'll come back to, this is very important. One thing that you would have noticed is you have these central regions and you have these tail regions, right? The tail regions are called localized states and the central regions are called extended states. So one important thing to remember is that these localized states do not contribute in conduction. It's only the electrons that fill these extended states, they contribute to conduction. These localized states are simply an effect of disorder in the system. So when we talk about conductive states, we only mean states in these extended regions, in these central regions. You'll notice that this is the Fermi level. Let's assume that these 4 Landau levels are filled and this one is empty. So the Fermi level lies at this point. Now, if you look at the Fermi level, the density of states at Fermi level has essentially gone to 0. There are no states at this point where the Fermi level is, right? And when you start to increase the B field, this Landau level will start to move up. And so at some point, the Fermi level will be right in the middle of the Landau level. And the density of states at the Fermi level will be higher at that point. So basically, an effect of this is that the density of states at the Fermi level also oscillates as you increase the B field. So now we come to the most important part, which is the integer quantum Hall effect. So this Landau quantization, the presence of energy gaps between consecutive Landau levels, and the presence of these localized states due to disorder leads to a very well-renowned effect called the integer quantum Hall effect. So I mentioned that, let's say you have an integer number of Landau levels filled, and the density for the system will be given by this expression, where this is the density in each Landau level times the number of Landau levels that are filled. And we had also calculated an expression for density from the Hall effect, remember? And it was a function of the transverse resistance, right? Everyone remembers that?
No.
Okay, good. So we can essentially equate the two, and what we find is that the Hall resistance in the presence of an integer number of filled Landau levels is constant. This is a very important expression. So the transverse resistance just depends on the Planck's constant and the electrical charge. Just J can be an integer 1, 2, 3, 4, etc. So this is a very important effect that you see quite a lot in 2D systems. and it's called the integer quantum Hall effect. The values at which the Hall resistance is quantized is so precise, it has such a precise value that it was even adopted as a new practical standard for electrical resistance. So this is an image that I took from the NIST website. This constant at which the Hall resistance is quantized is called the von Klitzing constant, RK, and it has a very precise value. It's really the practical standard for electrical resistance. I want to talk a little bit of a history. The integer quantum Hall effect was first discovered in the year 1980 in a silicon MOSFET sample. And the discovery is attributed to these three scientists. These two made the sample and this person measured the sample. This person, actually, Mike Pepper, was at Cambridge where I did my PhD. He actually started the semiconductor group where I did my PhD. So he made the sample, these two guys made the sample, but the Nobel Prize only just went to Klaus von Klitzing, who measured the sample in which they saw the quantum Hall effect. So I want to show you this data. Okay, this is the real demonstration of the quantum Hall effect. This is real data that I obtained for some of my samples. The red and the blue traces the red one stands for holes and the blue one stands for electrons. I had both electrons and holes in my sample. So if you just look at the staircase-like structure, you see, as a function of increasing magnetic field, the Hall resistance becomes constant at certain values. And these values correspond to these integer number of filled Landau levels. So this is nu equals 1 when you have at very high fields, when all the higher lying Landau levels have been depopulated and all the electrons just lie in nu equals 1 Landau level, then you observe this nu equals 1 quantum Hall plateau. And then nu equals 2, nu equals 3, and so on. So if you observe this kind of a staircase structure in the presence of high B fields in any sample, then that truly says that that sample is strictly two-dimensional. This effect is only there for a 2D sample. You don't see it for 3D samples. So this is a real test to say with surety that your system is two-dimensional. If you look at these oscillations, these are called Shubnikov. Sorry, I'm going to come back to this in a second. I want to first talk about these two conditions. This one we've already covered. This means that you have to have a high B field and a low disorder in the sample. But there's this other requirement that has to be met. And this basically means that the separation, this stands for the separation between the Landau levels. This separation has to be a lot more than the thermal energy of the sample. This is the thermal energy. So you don't observe this effect at room temperature, because at room temperature you have a lot of thermal broadening of the Landau levels. You have a very high thermal energy. And so you won't be able to resolve those discrete Landau levels. It's a quantum effect. So it has to be observed at very low temperatures. And this data was actually obtained at a temperature of 300 millikelvin in a cryostat. So these are very difficult measurements, low temperature measurements. It takes a lot to perform these experiments, but they are the real test of a 2D sample when you start to see these quantum effects which arise as a result of confinement. Yeah, so the other effect that happens in the longitudinal resistance at the same time when you see these plateaus in the transverse resistance are these oscillations. When the Hall resistance gets quantized, the longitudinal resistance exhibit these oscillations called Shubnikov-de-Haas oscillations. And I guess you can tell why these would happen, because we talked about these Landau levels, right? And so the longitudinal conduction occurs at the Fermi level. If you have no density of states at the Fermi level, then there will be no resistance at that point. So every time you have an integer number of Landau levels filled, the Hall resistance gets quantized, but the longitudinal resistance goes to 0, because the Fermi level lies in between 2 Landau levels, and the density of states is 0. You see it's 0 in between 2 Landau levels. So again, this is an important effect where you see the density of states going to 0 and the longitudinal resistance exhibiting minimas at the same time when you see these plateaus. So I want to pose a little question at this point just to see how much has been understood. We talked about disorder in the sample. We talked about the observation of these effects when an integer number of Landau levels are filled. How do you think the length of these plateaus, which corresponds to the time when you have an integer number of filled Landau levels, how does that correspond to the disorder in the sample? And to answer that, you will have to look at, again, this Landau level figure. These states, the tail states, are representative of the disorder, but they don't contribute to conduction. So if you have more disorder, you'll have wider tails, you'll have broader tails, but how will that affect the length of the plateaus? Would anyone like to answer that question? Just take any guess, maybe.
Disorder will increase the plateaus?
Right. Yes, that is the right answer. If you have more disorder, then the length of the plateaus will be longer. Does that make sense to everyone? When you have more disorder, you have more of these tails, but when the Fermi level moves through these tails, the number of Landau levels filled still stays an integer. It doesn't change the integer quantity of the filled Landau levels. So no matter, so at the time when the Fermi level is traversing these localized states, you still have an integer number of filled Landau levels. And that is the region which corresponds to the flat plateaus, right? So yeah, that is the right answer. If you have more disorder, if you have more of these localized tails, then you'll have longer plateaus and longer minimas in the Shubnikov-de-Haas, correct? Okay, so just a last couple of slides now. So I want to talk a little bit about Zeeman energy. I'm sure Dr. Incorvia has explained this concept in her class at some point. So when you apply a B field, then the B field also interacts with the orbital magnetic moment of the electrons, right? And you have a Zeeman energy corresponding to that. So the Zeeman energy is given by this, and it's the Zeeman energy for spin up and spin down states. So when you have a small Zeeman energy, the Landau levels are spin degenerate, which means that both spin up and spin down electrons, they stay in the same Landau level. So you only observe the Landau levels for even filling factors, because one Landau level holds both spin up and spin down. But the fact that I was able to observe these even odd numbered Landau levels, nu equals 3 and maybe also nu equals 5, then that just means that I had a significant amount of spin splitting between So my Landau levels were not spin degenerate, and I had quite a significant amount of Zeeman splitting in my system. And finally, this is the last slide. We've talked about the integer quantum Hall effect. There's also a relatively new discovery called the fractional quantum Hall effect, which is a much more complicated effect that I will not attempt to describe. So when you have very clean samples, you need very high mobility samples for the observation of this effect. You will start to see plateaus at even some fractional values of the Hall resistance. And this is an example where people have seen the fractional quantum Hall effect. These numbers represent the fractions of the Landau levels that are filled. So this is a relatively new discovery, which was made quite a few years later than the integer quantum Hall effect. And this discovery has also been awarded another Nobel Prize for its, yeah. So, yeah. I think that brings me to the, sorry, one more point is that the fractional quantum Hall effect arises because of interaction phenomena between the electrons. For the integer quantum Hall effect, we adopt a non-interacting picture, a non-interaction picture of the electrons. But to explain the fractional quantum Hall effect, you have to consider interaction phenomena between the electrons, which is what makes this effect a lot more complex to explain and understand. Okay, so I think that brings me, sorry, I finished a little bit earlier than the allotted time, but I will be very happy to take any questions either here, or you can also email me if you want to talk more about anything.